Let's now turn our attention to maybe the most important concept in all of Kubernetes, which is that of the pod. A quick recap. We've already seen how Kubernetes is a container orchestration system which runs on a cluster. That cluster is going to have a control plane which consists of processes running on one or more master nodes. Apart from these master nodes, the other nodes on the cluster are just worker nodes or just nodes or minions. Each of those worker nodes is going to host pods. A pod is an atomic unit of deployment and execution in the world of Kubernetes. Each pod is going to consist of one or more containers which are tightly coupled to each other. Kubernetes really only knows about pods, it doesn't know about individual containers. So you cannot run a container except through a pod. So again, a pod is going to be your way of creating individual containers and hosting them in a Kubernetes cluster. We can think of a pod as simply a sandbox, some part of the resources within a node which have been dedicated for one particular deployment. Pods come into existence when users of Kubernetes specify pod creation commands. They might do so either directly or indirectly using higher level constructs called replica sets, replication controllers, or deployments. We'll come to each of those in turn. But at heart, pods are created in response to user commands. A pod specification will include the containers which are to run inside that pod, as well as the ports on which those containers are going to be exposed. In general, pods will have a 1:1 relationship with containers, but that's not always the case. It is certainly possible for a pod to have more than one container running within it. If multiple containers run within a pod, they will be tightly coupled. They will share access to the same memory space. They will be able to connect to each other using localhost followed by the container ports. And they will also have common access to storage abstractions called volumes, which we have yet to introduce. So we should only have multiple containers running inside a pod if we explicitly want those containers to be tightly coupled with each other. That is not the usual use case. The common use case is to have just one container running inside a pod. One other important bit. A couple of times so far, we have alluded to pods as the atomic units of deployment and execution on Kubernetes. Let's make that precise. What exactly is atomic about a pod? A pod is atomic in two ways. The first is that the deployment of a pod is atomic. So it is never possible for only some of the containers within a pod to be deployed. Either all of the containers in a pod are up and running or none of them are. So that is the first respect in which a pod is atomic. The second is that a pod can only run on a single node. This is true of all pods, even those which contain multiple containers within the same pod. So it is never going to be the case that a pod runs on more than one node. What node a pod runs on? Well, that is a decision that is taken by the scheduler. Remember that the scheduler is a part of the control plane of the Kubernetes cluster. It is also possible that pod creation fails, and as we already saw, if such pod creation failures occur, they will be reported back by the kubelet, which runs on each of the nodes in the cluster, to the control plane, and the control plane will then decide what to do next. I find it helpful to think about pods in Kubernetes as being analogous to individual VM instances in a cloud world. For instance, if one virtual machine instance in your cloud application goes down, it is not going to be brought back up automatically. The manner in which auto healing, auto scaling, and such another features are provided is through additional higher level abstractions, notably replica sets, replication controllers, and deployments. We'll have a lot more to say about these, but again, the important point is that a pod by itself does not offer either auto healing or scaling. This means that if a pod crashes for whatever reason, the logic to detect that crash and to spin up a new pod is not going to lie within the pod specification. Rather, it is going to lie within the specification of some higher level construct like a replica set or a deployment. Also, pods are ephemeral. A pod can go away, it can be brought down, and each time this happens, the same pod is going to be spun up but with a different IP address. This is yet another reason why pods in the Kubernetes world are akin to virtual machines in the cloud world. Once we understand this ephemeral nature of pods, we also see the need for some of the other important constructs in Kubernetes. Because pods do not offer auto healing or scaling, we need a higher level construct which is called a replica set. Because pods do not offer versioning and they do not offer easy rollback of components, we need a further higher level construct called a deployment. Because the IP addresses associated with pods are ephemeral, we need some construct which offers a constant IP address and port for users or clients to hit the compute in a pod, and that gives rise to the need for services. And finally, because pods are ephemeral, they are going to need some backend abstraction for data or state to be set up within a pod. That abstraction is called a volume. We are going to have more to say on each one of these types of Kubernetes objects in just a little bit.